So let me redo the orbit stabilizer lemma. I didn't realize that it was not being, I mean, I was on mute and it was not being live custody on, which we've already, okay, so let G be a group acting on a set X. Then there is a then there is a bijective function epsilon. Let let X be inside X and write H for the stabilizer of X. Then and A for the orbit of X. Then there exists a bijective function epsilon from G mod H. Okay, so this is just cosets. H need not be normal to A. Okay. Sending the coset, some GH, this coset is sent to the element GX. This is what we need to prove. And so then we will see various applications of this today. That is, so the key point is to show that such a, this function, such a function is well defined. Okay, so we need to check that this function is well defined. Okay, that is, see, although we write GH, it is just a coset. Okay? It can be written as GH or some other G prime H. But the right side expression refers to that specific G, while the left side expression, it only appears to refer to that specific little g, doesn't actually, it just refers to a set. Okay, that is G prime H, then Gx is equal to G prime X. Okay, so we need to show this. So if GH is equal to G prime H, then there exists some H such that G prime is a GH. There exists some H in H such that this is true. So therefore, G prime X is GHX is H is in the stabilizer. So this is how. Okay. So first we are applying the composite function GH to X. We are applying the function corresponding to the product GH, which is the composite function. So we can write it as like this. And HX is, so therefore, epsilon is well defined. Okay. Now we need to check that it is injective and bijective and surjective. So surjectivity. So let x prime be inside A. Since A is the orbit of little x, there exists G such that G in G such that x prime is Gx. So then x prime is epsilon of Gh. So it is surjective. Injectivity. Injectivity is sort of the similar to the calculation for well-definedness.
Sir,
Similar.
could you just scroll up a bit?
Yeah. Which part do you want to see?
Yes, sir, this subjectivity part. Oh, okay, sir. Thank you.
A is the orbit of x, so therefore this is there, and then it just injectivity. So suppose that epsilon of Gh is equal to epsilon of G prime H. Okay. So that is Gx is equal to G prime X. Okay. So now, what does this mean? So this means so that is, we are saying that phi G prime of x is equal to phi G of x. Okay. So we would like to show that Gh is equal, I mean the coset Gh is equal to the coset G prime H, or in other words, we would like to show that G prime is in the coset Gh, or vice versa. That is enough. So this is what we have. So now let us apply the function phi G inverse. I mean, the function phi G inverse of x. Okay. These are bijective functions. So when we take inverse, we'll come back to the point where we started from. But what is this? This is phi G inverse is phi of G inverse. This is where the group action is. Composed with phi G prime of x. But this is again, this is just phi of G inverse product G prime. So this is what this means. Okay. So that is G inverse G prime is in the stabilizer. That is G prime is inside Gh. Therefore, G prime H is equal to Gh, which is what we needed to show for injectivity. Okay. So there is a bijective function from, and it is sort of natural with respect to this group action, that G mod H, the cosets of H, I mean, it is mapped to that element. This is a natural map that we have. So we would like to use this to study structure of groups and various things. So I just want to so most of today's discussion will revolve around this point. Okay, so yeah, actually, yeah, maybe I can do. Just give me 1 minute. I just want. So there are some corollaries of this thing. Actually, there's only one corollary of this. Other one is some generality. Corollary. Okay. Suppose G is a finite group. It doesn't really. I mean, one can do a computation only when it's finite group. So I'm going to just assume finite. So let us suppose that let G be a finite group. Acting on a finite set. Sorry, finite set. Acting on a set. Then let X be inside X. So let H be the stabilizer of X. And I'll just, okay, now onwards, I'll just write O sub X be the orbit of X. I mean, actually, so I just a piece of notation, maybe, but I would like to avoid using it in this lecture. Some textbooks use G dot X for the orbit. It's a very, I mean, and G sub X for the stabilizer. It's a very convenient notation, but except that when I'm lecturing on this tab, the subscript may not look. In a book, it is okay. Even on a board, I think it is okay. But I would like to avoid using this note. It's actually substantially more convenient and suggestive notation than whatever I am doing. But I just want to avoid orbit of X. Then cardinality of the orbit of X times order of H, order of G. Proof is just cardinality of the orbit of X is cardinality of G mod H by the orbits by the above theorem. Okay. But this is equal to order of H mod order of G mod order of H. So another useful thing which doesn't use orbit stabilizer lemma as such is the following remark. Let X be a set on which G acts. Okay. So let.
Sir?
Yeah.
So could you scroll up on just the last line?
Yeah. This is, I'm just using it's a finite group.
Yes, yeah.
Okay, that's, yeah. I mean, if you rewrite in some other fashion, this will be applicable to infinite groups also. But I don't think we will ever use it. So I don't want to fuss too much about that issue. Okay, G acts. Okay. So let us assume. Okay, suppose it. Okay. Let us even assume. Okay. Let us even assume it's a finite set. So again, we're going to use these things only for finite sets. Okay. So then there will be only finitely many orbits. Okay. So let O1, O2 up to OK be the orbits of this action. Okay. Then the cardinality of X is the sum of the cardinalities of the orbits. Okay. Again, this doesn't use anything much other than that the orbits, I mean, orbits are equivalence classes for an equivalence relation. Okay. So therefore, they are disjoint. Orbits are disjoint. Okay. When two orbits are disjoint, I mean, be the distinct orbits. Okay. So if two orbits are not the same, then they're disjoint. And for all X in X, there exists I such that X is in that orbit. I mean, there is always the orbit of X. So X, every element is in some orbit. So the union of the orbits is equal to X, and they're disjoint. So there's the cardinalities add up. That's all that is being stated. Okay. So X is the, maybe I should just, since this is the first time we're seeing all these things, X is the union of its orbits. Okay. OI intersect OJ is empty if I is different from J. That's what. Okay. So therefore, the cardinalities have to, I mean, this, the sum of the orbit sizes is equal to the sum of the size of the set. Again, it makes sense even if it's not a finite set. But this cardinal, what is called cardinal, again, which I don't want.
Sir, I'm not able to hear you.
Since we are going to use it, okay. So now we can now use it to learn something, some structure about groups.
So your voice is breaking
Am I?
occasionally.
Am I audible now? Hello?
Yes.
Could someone confirm that I'm
Yeah,
audible
yeah.
now?
Yes, sir, you're audible.
Yeah. Okay. Yeah. So let G be a finite group. And P a prime number, there exists an element G in G such that, I mean, whose order is P. Okay. In other words, G contains a subgroup of order P. So we will prove a stronger theorem later, I mean, later meaning next week, called Silo theorem. But so this is, I mean, this will follow from Silo theorem, but I want to just give a proof of this because it uses this orbit stabilizer lemma and this decomposition, that counting argument right away. Okay? So this is a good point to see an example of applying that to prove something about groups. Okay. So we'll have to set up, I mean, we'll prove, get this out of some group, I mean, expressing some group action on some set. Okay. So proof. Okay. So we will, okay, of course, we will not define, this is not the group that is going to act on anything. So we'll, okay, so that is part of the proof. Okay. So let X be the set of all P tuples from this group. Gi is inside G for all I, and not just any p tuple, only those whose product is in that order is identity. Okay. So this is the set of all. Okay. So for example, 1 1 1 1 1. Okay. So for example, a p tuple with is inside X. Okay. A p tuple where G repeats is inside X if and only if G to the P is identity. Okay. So it is such a G that we are going to look for. Okay. That such a G which is different from 1. That's what the proof will go to. Okay. And actually, okay. So this, how big is this set? So we can choose the first. Okay. So suppose the p tuple G1 through Gp is inside X. Then Gp is the inverse of the product of the first p minus 1 things. Right? That's what the definition is. So really we are choosing p minus 1 things freely and then writing the inverse of the product as the pth thing. Okay? So this is what. Okay, so we can choose the first p minus 1 things whichever way we want, but the pth thing is now determined. Okay? So therefore, X has order of G to the p minus 1 elements, and the point is that this is divisible by p. P divides G or order of G, so this is divisible by p. Okay. Any questions on this? Sorry, I'm just constantly checking to see that I'm connected and also my mic is on. Okay. I don't want to miss like last time. Is it clear?
Yes, sir.
Yeah. So this is what. Okay, so now we have constructed a set with of cardinality divisible by p, okay, and it's okay, this is what. So now on this we want a group to act. It is not G that is going to act on this. Okay? It's something. Okay? So I mean that is part of the cleverness of the proof. I mean not my proof. Okay, so it's whoever came up with this. I don't know if this itself was this was Cauchy's proof. This may have been rewritten after Silo's theorem was discovered. I do not know. So so now what we do? Okay. So now we will let. So there's one observation that we want to make. Suppose G1 through Gp is inside X, then G2 through Gp comma G1 is also inside X. Okay. So if you cyclically permute a p tuple that's already inside X, if you cyclically permute it, it will still be inside X. Okay. So therefore, X is closed under cyclic permutations, okay, of its elements. Okay. So this is a use. I mean, this is the observation based on which we're going to build. Okay. So this tells us that Z mod PZ acts on it, or the cyclic group. Okay. Okay. So therefore, Z mod PZ, okay, which is isomorphic to every cyclic group, acts on X. Okay. It is, I mean, just this observation tells us that we can actually rewrite this in terms of a group action. And what is the action? So now I will write it in the elaborate notation. Phi of 1 bar of G1 through Gp is whatever the cyclic permutation. G2 through Gp and then G1. So just remove the leftmost one, shift everything to the left, and put this leftmost one at the right end. Okay, so phi of 1 bar is this. Okay. So this is what we would. Okay, so we so this okay, so this is okay, so if you apply so I mean this is a group generated by 1 bar. Okay. So then 2 bar will be cyclic shift by 2, 3 bar will be cyclic shift by 3, and so on. So this is all that. Okay, so this is a group action. So I mean, please go through this to check that this is a group action. Okay. By orbit stabilizer lemma, okay, every orbit has cardinality divisible by sorry, cardinality dividing p. So every orbit has cardinality 1 or p. Okay. So let O. Okay, so I'm just going to enumerate the orbits. O1, O2, and OK be the distinct orbits. X is a finite set, so it's going to only have finitely many orbits of this action. Okay, without loss of generality, O1 is the orbit of 1. Is the orbit of not 1, the tuple 1, 1, 1. Okay. So we know that its orbit is yeah. So this is a cyclic permutation. So if you take a tuple where every entry is the same, its orbit is a singleton. Therefore, cardinality of O1 is 1. Under cyclic permutation, we don't get any new sequence. We just get this itself. Okay. So therefore, we get 1 plus cardinality of orbit 2 plus cardinality of orbit 3 plus and so on, cardinality of orbit k equals cardinality of x. Okay. Now this is divisible by p. Okay. This is not divisible by p. Okay. Therefore, there must exist an I. There must exist an I, 2 less than I less than k, such that ith orbit is not divisible by p. Right? Because if OI the cardinality of size of O2 is divisible by p, size of O3 is divisible by p, and all of these things are divisible by p. Left side would be a number which is 1 mod p, while right side is 0 mod p. So that can't happen. Therefore, there must exist something on the left side which is not divisible by p. Okay, that is. But of course, this is okay. Therefore, there must exist a G. Okay, so therefore, there exists some G1, G2 up to GP inside X, such that it is not identity. Because if it were identity, it would have been its orbit would have been covered, and its orbit would have been in O1. So it's not. This is not equal to that 1. This is not equal, and the orbit of G1 GP under cyclic permutation is just itself. Okay. This is what we have just concluded. So there must exist some element which is not the p tuple consisting of ones, okay, whose orbit under cyclic permutation consists of just that element. There can only be one answer to this, that there must exist a non-identity element who with a p tuple which is inside X. Just think about this. Therefore, it says that, so when you apply phi 1 bar, we will get G2, G3, etc. And that must equal this. So G2 must equal G1. Similarly, G3 must equal G2 and so on. Okay. So therefore, there exists G not equal to 1 such that G is inside X. But what does this mean? But we already observed this. This means that G to the P, G is not equal to 1 and G to the P is 1. This is what we want. There exists an element of order P. So this is a direct application of the orbit stabilizer lemma, from which one concluded that the orbit size has to divide the order of the group, and then just using the fact that the orbits form a partition of the set, so that the orbit sizes must add up to the size of the set. And one orbit is a singleton, therefore other orbits, at least, and the size of the set is divisible by P. Therefore, there must be another set which is also not divisible by P. But in this situation, not divisible by P forces it to be a singleton. So that is, so just to add here, this thing here implies that orbit size is a singleton. That orbit is a singleton. Okay. Because there are only two options, 1 or P, and if it's not divisible by P, it must be 1. Okay. So this is a application of things about group actions that we have discussed so far. Orbit stabilizer lemma and the fact that orbits form a partition. So this is okay. So this is a this is sometimes
hello,
used to.
Sir.
Yeah.
Sir, we know from the orbit stabilizer lemma that the order of the orbit must divide the order of the group, right?
Correct.
But here we actually have that P is a prime number dividing the order of the group.
No. That's what I said. It is not G acting on the set. It is Z mod P acting on a set. Z mod P acts on G. G does not act on.
Okay, sir. I see.
Yeah. The set X encodes all the group operations of G. But after that, we have forgotten about G. Is that clear?
Yes, sir.
Yeah. The group action is not G. The group in the group action is not G. It is Z mod P. The set is constructed. The set is a subset of G to the P. Yeah.
Oh, so as Z mod PZ has order P, so that's why this.
Yes.
Okay.
Yes. It is orbit stabilizer lemma for. So maybe I should just emphasize. This is the action. Okay. Yeah. No. Yeah. Is that clear? Okay. So this has various applications in trying to say that there are elements of. There are certain subgroups of certain size. Okay. But we will come back to these things. The full-fledged form in terms of zero theorems by next week. Okay. Okay. So now I want to proceed with. So there is another application. There are various things of this orbit stabilizer lemma and thing. That's the next step that I want to do. It is called class equation. that is again saying something about.
Sir, we can't hear you.
Yeah. About structure of.
Sir, your voice is breaking.
Spoken anything. Hello? Hello?
Yes, sir. Now it's fine. Yes.
Yeah. So I had not said anything. I wrote class equation, and then I didn't say anything. Okay. So now this is again studying something about a group. So let G be a group, finite group. Okay. G acts on itself by conjugation. Okay. That is phi G of some H is G H G inverse. Okay. So so this is this tells us some information about groups. So when would an H be have a singleton orbit? Okay. So let H be inside G. I mean, this is for H for all G inside G for all H inside G. Okay. So the set as well as the group element, they're, I mean, set is same as a group. Okay. So this is okay. Then the orbit of H equals the singleton H if and only if phi G H is equal to H for all G inside G, if and only if GH G inverse is equal to H for all G inside G, if and only if GH is equal to HG for all G inside G. Okay. In other words, it is H commutes with every element. Okay. And the set of subgroup, the set of elements with this property. So it's called the center G, denoted ZG, is the set okay, is a set of all elements H, the set H commutes with every G in G. This is then observation ZG is a normal subgroup. Okay. So I just want to say some. I mean, we are not. I will not dwell on this topic. I mean, will not develop anything mathematical about this. See, given a finite group, okay, there is a. I mean, it was a very long-standing problem that given a number, given an integer n, do we know all the finite subgroups of that size? So that itself can be broken up into a simpler problem called, if we can, so if you have a group, so I'm not going to write in it these things down because I am not going to do any mathematics with it. Just to sort of give a context for proving such results. That's all. Okay. So if you have a finite subgroup, and then you have a normal subgroup, then in some way you can express it. You can sort of build the given group from the normal subgroup and the quotient group, both of which are smaller. So because of this, there was a long-standing problem in group theory called the classification of finite simple groups. Simple means groups that don't have a normal subgroup. This must have taken thousands of pages for the full proof. Okay, so the classification of finite simple groups, I think it is in printed pages, some 4 books or something. This is after doing all the elementary things that we would do in courses and elementary. It took, I think that whole publication is like 4 volumes of book. Okay. So it's a humongous work. So the class. So back to saying, the simple group is one that does not have normal subgroups. Okay. So the general philosophy being, if a group has a normal subgroup, then we sort of understand what that normal subgroup, what that group is, because we have information about smaller groups. Okay. The quotient group as well as a normal subgroup. So therefore, if we are given a group, the knowledge that it has a normal subgroup should make us happy. I'm speaking figuratively. Okay, so that's the sort of reason why. Okay, if there is a way to identify normal subgroups, we would try to use it, and then somehow let's hope that this will simplify the problem that we are studying. Okay, so this is just a general philosophy. It's not a. Okay, so now we are saying that the center is a normal subgroup. Okay, I'm not saying that the center is actually non-trivial. Okay? Of course, 1 is there inside this. Okay, so let us, maybe I'll call it proposition. Since I call it normal subgroup, it deserves to be called a proposition. Proof. 1 is inside ZG, since 1 times G is G times 1 for all G inside G. Now, suppose H1. Okay, so I'll do a different trick this time. Yes. Okay, maybe I should not. Okay, not in this. Okay, I'll do it separately. Then H1, H2 of G, not of, this is just a group product. H1, H2 G is H1, H2 G, which is H1 G, H2, which is H1 G, H2, which is G, H1, H2. Okay. So H1, H2 is inside. And H1 inverse G. Okay. So this, sorry, where am I? Yeah, sorry, this requires a little bit more. So now note that GH1 is HG1, H1G, right? Multiply on the left by H1 inverse. Multiply on the right by H1 inverse. Okay. So therefore, H1, this is again for all G. Again, this is also for all G. That is why this is there. Therefore, H1 inverse is inside this. Okay. So therefore, is a subgroup. Of course, I'm not saying that it is a non-trivial. I mean, it is strictly. I mean, it could just be the singleton containing the identity. That I am not saying. Or if G is abelian, it could be all of G. But I'm okay. Okay, so now we need to prove the normality. So now let H be inside the center and G be inside G. So then G H G inverse is H. Therefore, ZG is normal. So this is a normal subgroup. The center is a normal subgroup of a group. Okay. Maybe some remark. Whatever I just said. Okay. It is not clear. I mean, it is not necessary that ZG is strictly bigger than the identity element. Okay. And two, if G is abelian, I mean, in fact, G is abelian if and only if the center of G is G. Okay. Every element commutes with every other element. So for non-abelian groups, I mean, this might yield us some information. Okay, so that is what I want to. I mean, okay. So this is what we want to do now. So using this, I mean, so we want to discuss this class equation, and from that we would like to understand something about some non-abelian groups. Okay, so all of this comes in the context of G acting on itself by conjugation. Okay. Something is in the center precisely when that orbit is a singleton. So what is called the class equation of G so this is just saying that G, I mean, this is for, okay. So it is in this context. G acts on itself by conjugation. The orbit product, the orbits are the conjugacy classes of the various elements. Each element has a conjugacy class. Those elements that are conjugate to it. Okay. These are called the conjugacy classes. Okay. And so let C1 up to Ck be the distinct conjugacy classes. So first of all, each conjugacy class, the size of it must divide the order of the group. Okay. From the orbit stabilizer lemma. Okay. Ci divides order of the group. And I mean, this is not for all. Further, cardinality of the sum of the cardinalities of the CIs must be order of the group. Okay. So these are just saying that the conjugacy classes are orbits. Okay. So the union is the whole set. They are pairwise disjoint. Therefore, the cardinalities add up to the order of the group. So this is what is called. Okay. So we would typically write order of G is this thing. see. Okay, so I'll give examples. This looks like some abstractly writing something. So this expression is
Yeah,
called
but this is
classic.
true for a general action also, right?
It's true for general action, but when we say class equation, we mean only for this conjugacy, I mean,
Oh, okay.
convention. I mean, which is
Okay.
yeah, it is true. We haven't done it. Yeah, I mean whatever we said is true, but now I mean conjugacy classes. Okay? It's called the class equation of. Okay, just give me a minute. I just need to get my notebook because I need to make sure I get the calc. Yeah. Okay. So I want to use this now to in two examples. One is quite similar to the Cauchy theorem. So let me do that first. Okay. So examples. One. It's called finite P. I'll define what finite P groups. So a group G is called a P group. P a prime. If for all G in G, the order of G is a power of. Okay. So every element has finite order, and it is a power of P. As such, I am not saying that G itself is a finite group, but of course, we will worry only about finite groups. Okay. So a finite group G is a P group if and only if order of G is a power of P. Okay. So let us. So if order of G is not a power of P, then there must be some other prime Q that divides order of P, and then there must be an element of order Q in that group. Okay, so it's not a P group. Conversely, if this is the case, then order of any element must divide P, so therefore it must be a P group. So let us prove this proposition. Proof. Okay. If let G be inside G, so G is an element of a group which is an order power of P. Therefore, order of G divides a power of P. This means that order of G is a power of P. Okay. So therefore G is a P group. Only if. Okay. By way of contradiction, assume that Q is a prime. Q divides order of G. Q is different from P. So this means that there exists an element G inside G of order Q, which implies that G is not a P group. Contradiction. I mean, yeah, we do not write as a contradiction. We can say that Q be a prime that divides the order of G. There exists an element, therefore that would force Q to be P. Okay? And that is this is by
Can you scroll up to the this is it. Oh yeah, sir.
so the definition is that every element has order power of P, but for a finite group, it is just equivalent to saying that the group has order power of P. So this is what we will use. So what would the class equation of? So let C1 up to Ck be the conjugacy classes. Okay, so let G be a finite P group. This is the end of the proof. Let G be a finite P group. Okay. And let these be the conjugacy classes in G, be the distinct conjugacy classes. Okay. So C, I mean, this is a disjoint, I mean, this is a partition of G. Okay. So then C1 to Ck is order of G. This is divisible by P. Okay. Without loss of generality, C1 is the conjugacy class of 1. Okay. So therefore, C1 is a set of all things of the form G1 G inverse G is inside G. This is what we mean by conjugacy class. Okay. Take an element and look at all things of the form G times that element times G inverse as G varies in that. But this is just okay. Okay. So therefore, cardinality of C1 is 1. Okay. So now we use exactly the same argument. Okay. That the right side is divisible by P. In the sum expression on the left side, one of the numbers is not divisible by P. Therefore, there must be another number which is not divisible by P. Sorry, just a minute. Correct. Sorry, that is enough. Okay, right. So there exists I such that, sorry, I for a minute I got is not divisible by P. Okay, but what are the options for Ci? Okay. Note that for each I, this thing divides G. It is a conjugacy class, so it's a class on, it's an orbit. Okay, so by orbit stabilizer lemma, this divides the order of the group. Okay, therefore, Ci is a power of P for all I. Okay, maybe I should use J here for all J. Okay. Therefore, for this particular I, it must be 1. Therefore, there exists I such that Ci is 1. So the only options for the cardinalities of the conjugacy classes are powers of P. And there exists, so this I is greater than or equal to 2. Right? we look at the sum, the right side is divisible by P. In the left side, the leftmost one is not divisible by P. Therefore, there must be something else also that is not divisible by P. That is, there exists an I greater than or equal to 2 such that this is not divisible by P. Okay? But on thinking about it further, we see that if it is not divisible by P, it must be 1 because otherwise it is a power of P. I greater than or equal to 2. Okay? But what does that mean? It means that there exists an element, that is, there exists some H inside G, H different from 1, because this is a conjugacy class of some other element, not that of 1, such that GH G inverse is equal to H for all G inside G. That is, the center of the group is not identity. There exists some element H, not identity, which commutes with everything. Okay? Therefore, the conclusion is that, that is, G has a non-trivial center. Okay, it could be that G is abelian and all of G is the center. But even if G is not abelian, it is not very difficult to come up with order of P square. I don't know. P square, no. P cube. So we see we have not. The semester. In a course that had more group theory stuff, we could probably have proved various things about small sizes, P square, P cube, and things like that. But now we are sort of out of time. So G has a non-trivial center. So there are groups of order P cube, okay, which are non-abelian, but still they will have a non-trivial center. Or in other words, therefore, G, okay, is not a simple group. Okay. As I said, I am not going to elaborate on this point further, but this is that is, G has a non-trivial normal subgroup. Okay, that is not really a. Okay, maybe that is not. If G itself is a cyclic group of order P, this claim is not true. So let me not. Right. Okay, let me just stop it here. But if I say anything about non-triviality of the normal subgroups, then the question will come as to whether. So I would need, for such a statement, I would need to exclude cyclic group of order P, okay, because that is a simple group. Yeah. So
Hello, sir.
Yeah.
Sir, in the proposition that a finite group is a P group, if and only if cardinality of G is a power of P.
Yeah.
There, in the second part, we just assume that G is not a power of P, and then we prove that G is, I mean, cardinality of G is not a power of P, and then we prove that G is not a P group, right?
Yeah, yeah.
So, but isn't it the same as the if part?
What did I prove? Sorry. Maybe did I get the direction wrong? I assume that I proved that if order of P is a power of P, then every element's order is a power of P. Then I assume that order of G is not a power of P.
Yes, sir. It's fine.
This is
It's
correct.
fine. Yes, sir.
This is correct. Yeah.
Yes,
Yeah.
sir. Yes.
Yeah. It is possible, but this time I have not made a mistake. Yeah. But yeah.
Sir, can I ask a question regarding this quiz? Yes. So there is a question regarding finding the cycles of the action of the subgroup of S3 on S3. Two questions, sir.
Yeah.
So and that in that case, the cycles were just the cosets.
Correct.
Of the subgroup. So, sir, does that follow from what we did on operation of cosets? On last.
No. Operation cosets is sort of opposite direction. See, you have G inside H and H acting on G by translation. The quiz problem and things that we discussed last week were related to that. Operation on coset is other way around. G acts on the set of cosets.
Okay, sir. So
yeah, they are. Yeah.
Does this is this thing true in general? Like,
what is true in general?
So in this case, like the action of subgroup divided in, we partitioned the group into cycles, and the cycles were the same as the cosets of the subgroup.
Okay, maybe let me. Can I? I just want to do one more example. Then Can I come to your question after that?
Yeah. Okay, sir.
Yeah. I just want to do quickly this class equation for S3. Okay. And then so one is asking how many, what are the sizes of the conjugacy classes? Okay, so this is 6. S3 has an element of order 3, the cycle 1, 2, 3, okay, and then it's square, so 1, 3, 2, and okay, so S3 is identity cycle 1, 2, cycle 1, 3, cycle 2, 3, then cycle 1, 2, 3, and cycle 1, 3. Okay. So what are the conjugacy classes of these elements? Actually, maybe if I do this, I will not. Maybe I will do this in the next class. Let me answer your question.
But the transpositions actually commute, right? So
no, transpositions commute.
I mean the
square is.
Sorry, sir.
Yeah, no, but let me answer. I think there is. I want to clarify that question. I think there's some confusion about what is a group and what is a set in that question that somebody asked. So let me answer that, okay? Because I think if I take this, this will take me all of the remaining 7-8 minutes. Okay, so I will do this next time. In fact, I can. This is not even. This is okay. So back to your question. Sorry. Okay. So you were asking. So G is a group, and H is a subgroup. Okay. And so from what I understood, you were asking whether the action of H on G, where phi H of G equals HG, and action of G on G mod H. Let me call it psi G of some AH is equal to GA. Okay. Yeah. So you are asking whether these are the same. Is that did I understand your question?
No, sir. Like in the first case, you have an action of H on G. So that action will partition G into cycles.
Correct.
So will that cycles be the same?
Not cycle cosets. Not cycles, cosets, right?
I mean, the action of a group on a set partitions the set into cycles, right?
Set into orbits.
Yeah. Sorry. Orbits. Okay. Sorry.
Yeah, and orbits are precisely the cosets.
Yeah. So the orbits is okay, sir. Yeah. So is that?
No. Yeah. So partitions G
into orbits.
Yeah, into orbits, but these are just cosets of H.
Okay. So is that trivial? It's just the definition.
What is definition?
I mean, does this just
follow? Are the orbits same as the cosets of H? Is that the definition of your question?
Yeah. Yeah. Is it just
that you have to check? Okay.
Okay. So, yeah.
let me just explain. So what are we saying? We are saying that so some G is inside here, okay? And then we want to look at the set phi H of G as H varies inside H. That's what the orbit means, right? You take an element of the set and let the group run over it and get to every possible place. That's the orbit, right? But this is just HG, H inside H. And so this is the right coset. Yeah, so the orbits, so the orbit, therefore, orbits are right cosets of H. Yeah.
So like if it's clear, sir. So if this has to be equal to the left cosets, then it has to be normal.
That is true. But these are sort of independent things.
Yes.
Don't. So this is just H acting on G, and the orbits are this. This is G acting on G mod H, which is actually the space of left cosets.
Okay. So in that question, like H was normal, so the orbits were equal.
But that question, if you got one of the questions was the 3 cycle, right?
Yeah,
so it was normal. Yeah, so that was just it was probably just so happened that right coset is left coset, but this particular setup requires neither condition.
Okay.
Yeah, I hope it clarifies.
Yeah, yes, thanks.
So I'll stop here because so I will do the S3. Maybe I'll put this in exercise because it's not it's not very difficult. Just to find out conjugacy classes in S3 is not that difficult question. Okay, because we can just sort of just do by hand. I mean, what is 1 2 times 1 2 3 times 1 2 inverse? I mean, 1 2 inverse is just 1 2. Okay. So then, so writing like that, maybe I'll do an exercise. I'll give you some practice on computing with cycles and permutation groups instead of me doing it. Okay. So next week we will start proving zero theorem. I'll stop. Yeah.
That's a general question. Do we have linear algebra in the NSEM?
Yes. The final exam is for the whole semester.
Oh, okay.